All right, in this video, we're ready to talk about the operations of vectors, but now algebraically. So we have vectors v and w defined in component form, and k is any scalar. Now, to add or subtract two vectors, we'll take vector v plus vector w, which is v1, v2, plus w1, w2. And we're simply going to add corresponding components. So this would be v1 plus w1, comma v2 plus w2. So pretty straightforward. Subtraction is the same way, so we'll just go ahead and say a plus or minus there, and we can add the plus or minus to the simplified form as well. So there's a vector addition and subtraction algebraically when our vectors are in component form. For scalar multiplication, if k is a scalar and we multiply it by vector v, then that's k times v1, v2, and we're just simply going to distribute the scalar into each component of the vector. So there's scalar multiplication. Now there's also an interesting operation called the dot product now for vectors, and that means if we take vector v and we dot it with vector w, v1, v2 dotted with w1, w2, this is going to end up being v1, w1 plus v2, w2. So we put together essentially a linear combination here of the individual components. So the thing to walk away with from this discussion, though, is because it's definitely not the most complicated idea. However, the big thing to walk away with from here is when you add or subtract two vectors, you end up with a vector. When there's a scalar multiple involved like this, you walk away with a vector. But when you dot two vectors, what you finish up with is actually a scalar. So that is not a vector. When you dot two things, you end up with a scalar. And that's pretty interesting because that's going to now allow us to apply this dot product in an interesting calculation here in just a second. So you just finished working a couple of examples with the operations algebraically in vectors. Now we're going to look at an interesting application here where we find the angle between two vectors. And so the formula for this would be cosine theta equals v dot w divided by magnitude of v, magnitude of w. So in the example we're going to look at, we're going to be given vector v as -2, -5, and vector w as 1, -9. Now, I'm not going to draw this to scale, but essentially what's being asked of us is, if this is v and this is w, to go ahead and find the angle between them. So let me go ahead and get this set up as cosine theta equals -2, -5, dotted with 1, -9, divided by the magnitude of v, which is -2 squared plus -5 squared, times the magnitude of w, which is 1 squared plus -9 squared. So, for cosine of theta, if we dot these two things, we're going to get -2 plus a 45, and then under the first radical, that's going to be a square root of 29, and under the second, a square root of 82. So I'll just clean this up a little bit. It's clearly going to be a calculator problem, but I'll say 43 over root 29 root 82, and then inverse cosine of 43 over root 29 and root 82. And so we're ready to punch this in a calculator. Once you punch this in a calculator, you find out that the angle between the two vectors, the theta, should be 28.1 degrees. Now, what's most interesting about the angle between two vectors is the cases of when they're parallel, perpendicular, or neither. Now, we've already discussed knowing that two vectors are parallel if and only if they're scalar multiples of one another. Now, to determine if two vectors are parallel, this is actually pretty interesting. So we know that two vectors are parallel if the angle between them is 90 degrees, or pi over 2. So if I look at the formula from before, cosine of pi over 2, Well, cosine of pi over 2 is equal to 0. But I also know that from the dot product, it has to equal this. So if I take v dot w divided by magnitude of v, magnitude of w, and I view this now as an equation, if I multiply both sides by the magnitude of v, magnitude of w, so if I multiply both sides of this equation by that, what I've really concluded is that two angles are separated by 90 degrees, or the angle between them is pi over 2, when v dot w is equal to 0. So when the dot product of the two vectors is equal to 0, then the angle between them is pi over 2. In other words, they're perpendicular. So I'll give you guys a few minutes to take a look at the examples then in the notes and see if you can show sufficient work based upon this discussion in determining whether vectors are parallel, perpendicular, or neither. So now we're ready to talk about unit vectors. And a unit vector is a vector with a magnitude of 1, so a length of 1. And to take a vector that doesn't have a magnitude of 1 and to make it have a magnitude of 1, make it into a unit vector, the process is to normalize the vector. And so to normalize and create a unit vector, we take vector v and we multiply by 1 over its magnitude. So this formula here will take vector v, which is not a unit vector, and turn it into 1. So the example we're going to look at, example 4, tells us, okay, we've got vector v here at 5, negative 4. And we want to find a vector of length 8 that points in the opposite direction as this. Now, before I get into the actual specifics of the problem, I do want to convince you of the formula working. And so if I go ahead and I take now 1 over the square root of 25 plus 16, and I multiply this by vector v, which is 5, negative 4, that's going to give us a result of 5 over the square root of 41 and negative 4 over the square root of 41. So again, we're claiming this is now a unit vector. So to confirm this, and this isn't really, again, part of the problem, but I just want to show you how this works. If I take the magnitude of our assumed unit vector, that's going to be 5 over root 41 squared plus negative 4 over root 41 squared, which would be 25 over 41 plus 16 over 41, all square rooted, which is 41 over 41, which is equal to 1, as we hoped. So again, that's just to convince you the formula works. Now, it's also helpful in solving this problem, because if our job is to find a vector of length 8, and this has length 1, then all I need to do is come over and multiply the unit vector by 8. So now, when we distribute this, we'll get 40 over root 41 and negative 32 over root 41. And we have a vector now that points in the same direction as this, but with a magnitude of 8. To find a vector that points in the opposite direction of this, all we would have to do now is put a negative out in front of it. When we put the negative out in front and we distribute, we come up with a final answer of negative 40 over root 41 and a positive 32 over root 41. So this vector here is of length 8 and points in the opposite direction as the original. So we'll go ahead and talk about standard unit vectors at this point. And for us, the two standard unit vectors that we're going to talk about would be vectors I and j. So vector I would be on the x-axis defined by 1, 0, meaning the terminal point would be at 1, 0. For us, the notation would be vector 1, 0. J would be along the y-axis. So this would be vector j denoted by 0, 1. And again, the terminal point would be 0, 1 as well. So standard unit vectors come into play because of a very important property. The property says that every single vector can be represented by a linear combination of standard unit vectors. So every vector can be represented by a linear combination of standard unit vectors. So in the example we're going to take a look at, we've got 2, 3. Now, my first step as representing this in a linear combination of standard unit vectors is to just go ahead and split it apart into 2, 0 plus 0, 3, which you can see is just a different representation of the same thing. I'll also go ahead now and be able to take out a scalar from each one of these. And you can see in doing so now, we're left with vector I and vector j. So 2i plus 3j. So the original vector is now represented as a linear combination of standard unit vectors.